Okay, welcome back in. Do we like the light in the room? Do we want another light on? Maybe? You know what? Adjust our eyes. Well, there it is. Okay, let's just talk a little bit more about completeness. I think people see this sort of definition and they think, like, what the heck is that? So this one isn't as intuitive maybe as the sufficient, like what a sufficient statistic or a minimal sufficient statistic. I think we all understand what that stuff is intuitively, probably more than the technical definition. So sufficient statistic has all the information about the parameter theta. Makes sense. So I get that concept. Why is the technical definition a ratio? You know, that conditional distribution doesn't depend on theta. The way I like to think about it technically is both shapes are the same of the function. And I kind of like to think about the likelihood principle through it. That I'm really just talking about the likelihood shapes are the same. And I think that is what's the important thing, but I'm taking it a step too far and jumping over to that where sufficient, like the likelihood principle encompasses the sufficiency principle. So it's not to say that there aren't other methods that encompass the sufficiency principle. The likelihood principle gives us a little bit more, and then it conditions on the exact data set, and not looking over more extrema. And that was the example that we used that shows that if you're using your data and something you never observed that is unlikely to occur in the first place, why should I use that to make judgments about theta? And I can kind of understand that, but then I need the technicalities to really show me that why it might be a good idea or why it might not be a good idea. And we'll talk about more about that in chapter 8. So if you like controlling error rates and you know the process of everything, you want to fix a type 1 error rate and minimize the type 2, then there's some methodology for you. And I think that can be a useful paradigm when you have a well-controlled experiment or a conveyor belt. You know, something that's truly frequent test and you really want to monitor those rates. So it could be a good idea, and it depends on the context. So I think there's a lot of things that are roughly intuitive. We have to check the technicalities of it all. This is the backwards from that. This is like a technical condition, and then we get things out of it. And that's the way they explain it in the book. And it's like, what is this technical condition? So there's two different theorems in the book that are important. We discussed Bassu's theorem, something about ancillary statistics, and we're talking about the non-overlap of min-sufficient statistics with ancillary statistics. In the problem in the book, the problem I gave you for homework, if you've sat down and looked through it and glanced at the solution manual and figured out how to do that, you figure out that if things aren't complete, there's a way of setting up a test statistic that has this property. If there is an ancillary statistic out there that encompasses the min-sufficient statistic, you can always use that to construct an estimator that's not complete. So, and I'll let you think about that a little bit more. There's a lot to think about with all these concepts. Completeness tells us something that it seems mathematically strange, but I assure you there is some intuition behind this. So I'm going to try to go backwards and show you what happens if a test statistic is not complete. What could happen and why it might be important. I think the way they explain it in the book is this is a technical criterion so that we can prove Bassu's theorem. And there's another theorem in the book in chapter 7 called the Lehmann-Scheffé theorem, and I'll allude to it, although we're not going to study that one in this class too, but I do think it's important in an advanced inference class you'd spend some time on it. Does anybody know what Lehmann-Scheffé says? It's not me, so it's a different, it has an H in two ends. David?
For a parameter is complete and sufficient and its expectation is equal to the parameter, then it will be the minimum unbiased, minimum variance unbiased.
Yeah. So whatever the bias level is on it, if it actually is the parameter and it's unbiased itself, what David said, if you know the statistic itself is complete, then you know automatically it's min variance. We're not going to prove that, but in some sense it's optimal. So it might be unbiased or have some bias level that's fixed. You might want to make that unbiased. And if you knew it was complete, you could automatically jump to some optimality criteria. So that is useful. So that's kind of cool. And it also tells us that there's only one of those estimators out there. So that's what David said. It's also unique. We're not going to study that because I think the mathematical mechanics is going to take us 2 or 3 days that we don't want to necessarily spend. And what I want to give you in return is the EM algorithm. So an algorithm you are bound to hear about in different settings in your career as an optimizer or a statistician or anything like that. And I'd like you to code that thing up. So I want to give you a tool instead. Let's just see what happens when things are not complete. So instead of talking about completeness, let's consider a non-complete statistic. So consider 2 functions. This is not my argument. This is a well-known argument. I wish that they led with it in the book, so I'm just going to present it to you. But consider 2 functions. I'm going to say g1 t of x and g2 t of x. So I'm still in the same framework where I'm taking some function over t of x, some test statistic. So when we're talking about this right here, the hard part of this is this has to be for any function, all functions, g. So I just need to find one function such that this is not true for us to say that the test statistic is not complete. And that can be hard to do. The book, in the example that I gave you to work through on homework, you always work this out through the ancillary statistic. You can always use an ancillary statistic to build a function g such that that criterion is true. So that's always true, and the book will show you how to do that. I.e., you take whatever your test function is, and then you subtract off its mean. And you'll always, in the case where you're using an ancillary statistic as that test function, you can always do that to show something is not complete. So if there's an ancillary statistic that incorporates the minimal sufficient statistic. So you can basically unwind Basu's theorem to show how to show something is not complete. And I think that's what they do in the example. But consider these 2 functions right here. And I'm going to say such that the expectation of both functions of t of x, this is going to be equal to theta. So I'm imagining theta is my parameter in the thing. So I have xi's coming from an f that's conditioned on some parameter theta. So theta is our parameters of interest. And expectation of g2 tx is also theta. And I'm going to say in a second, g1 and g2 are not the same functions. So obviously, if the functions are the same functions, there's no problem on the board. But already this would be weird if this happened. If this was true for all values of theta, so keep in mind our xi's are coming from some model. I'm kind of writing it down like it looks IID. It doesn't have to be IID. But if we imagine IID, we've got some xi's coming out of some model. And if this was true with 2 different functions, and it's always equal to theta, that would be super strange. That there's 2 functions out there that could do this. I'll kind of point out that's the same strangeness we see over here, right here. That if this was true, right here, so if that was true, and this weren't true, that would be weird. So that would be something super strange to me. So I'll just write that down. If star is true, but double star is not true, that's strange. reason it's strange is because in my setup, I can change theta. So and generate new x's. And then check this criterion, that thing's 0. But for some just arbitrary function, this isn't 0. Right here, that's very bizarre that this would happen. We can already see that if this thing were 0 and identically 0, of course that's true. But if this were true and that weren't true, that's really bizarre that for any theta, I can wiggle theta around and this is still true. That's really strange to design some estimator that depends on the data. It fluctuates. So if this weren't identically 0, then this thing would be fluctuating around. Obviously, if I multiplied n by 0, it would always be 0, and I would never change anything. But if that were just always 0, and I fluctuated theta around, and that weren't 0, that would be really strange that it always comes up to be identically 0. Super strange. This is also strange that that would happen. That for any theta, and I have these two different functions that are not identically 0 themselves, and they're always giving me back theta, that's weird that there would be two estimation procedures that are different, but they're always giving us back the same thing in expectation. That would be super weird. You can always set that up with an ancillary statistic that depends on a minimal sufficient statistic. So that's the homework exercise, is to at least demonstrate how you do it. You take the test statistic and subtract off its mean, and that will always work. And that's the example in the book. So I would say this is kind of weird that this would happen. Let's make our statement that these two functions are not the same. I'm going to say the probability of G1 x is not equal to G2 x. Now I'm going to say this thing is positive, greater than 0, strictly greater. So this is a positive probability that they're different. So that's just a statement that they're different. I could rewrite this like this and say something like G1 x minus G2x is not equal to 0, and this is equal to 1, right here. So they're not the same. So, and I can measure that. You might want to take some limits. If you want to take the limit inside, then you're making an almost sure statement about it. So we'll just omit the limits. Keep this as a simple concept. So basically it's saying that there's two functions out there that estimate the exact same thing. I could form a new estimator. So from this I could say G1 x minus G2 x is unbiased for 0. But this is not 0. Take the difference between these two things, I drop it into that expectation. Expectation is a linear operator, and you can see that it's theta minus theta. So that's 0 in expectation. For that to be true, and the g functions not to be 0 themselves, and the difference between these two functions is not 0, but it's always 0 in the expectation, that would be really weird. And so we don't like that. What we would like in statistics is for us to have one function that does this. It's a unique function, and we'd like a little bit more. We'd like to know that that function is good. And so that's what Lehman-Schiffer says, is that it's minimal variance if it is actually complete and this doesn't happen. So this is just kind of a rehashing of completeness in reverse. So we could show that if this is the case, then T of x is not complete. So complete statistics don't do this. And that's kind of cool. So what it says is if your stat is complete and insufficient, we should all agree to use it. And we'll have good estimation properties out of it. And there's unique estimators that we get out of it, and those unique estimators are optimal in some sense. So I tend to think this is probably better to leave for an advanced inference class once you kind of appreciate some of this stuff a little bit more. But this is at least why we might like completeness. At least one reason why we might like completeness.
That second line inside the box, showing that G1x doesn't always equal G2x, and anything else that they're not zero.
Okay, I'll say not zero. So in the limit, you might say that this is 1, but yeah, this is not 0. So as we got a lot of data, we'd probably be able to tell for certainty that those functions aren't the same functions. So that was the limit part that I'm leaving out. So that is correct. That's where the limit would be important. But basically, I'm just saying those two functions are not the same as each other. So anyway, that's why we might like completeness. So it's not a totally vacuous concept so that I know something about ancillarity. It does come up later. If you do happen to read through that part of the textbook and study stack exchange and have a more advanced book, if I do ask you to show that something is unbiased and minimal variance, if you do take the path and show me that it's a complete statistic, which might be harder to do, I'll give you credit. It's a correct answer. And every once in a while, every 3 years, somebody will pull out an answer like that. David's gonna do that, right? So just to be super impressive, I can see Dylan like doing this. I'm just gonna do this weird proof, make it seem more technical. I know lots of stuff. I'm not gonna ask you to do anything in this class. What I'm gonna ask you to do is work out the variance of estimators and show that maybe you know that it's not meeting the minimal bound or something like that. And then you can say there's some estimator that beats us. Here's kind of where this can be kind of more interesting is in that example with the range and the mid-range that we studied last time, and we showed that that minimal sufficient statistic was not complete. So R was an ancillary statistic, is why we figured that part out. And the homework example takes you one step further in showing that that's not complete, but i.e. it's not complete because of Dassu's theorem. You can show it more technically by just working through the definition. What it tells us is it's really hard to figure out what an optimal estimator is. So we might not know what the lower bounds are. And so that could be, that basically means you need to put more constraints on the problem. So in some class of estimators, it's optimal at least within that class. But could anybody ever deliver another estimator that beats you out that's outside of the class? And the answer could be yes. I actually see that as an opportunity. I really like when things like that happen because it means you could come up with something good and 2 years later you could come up with something that's better and 2 years later you could come up with something maybe better than that. And you could explain in what sense and in what context they're a little bit better. So, of course, it's kind of nice in problems that we all agree on what the best is. So an example like X bar estimating mu in a normal distribution, you could verify that that's a complete statistic. What it basically says is we're all going to agree. So I think there is something to all of this, but I'm not going to take it that deep in this class. So that's about all I want to say about completeness. So it's not just a technical criterion, it omits against this thing that I wrote on the board, that there's two estimators out there that are simultaneously unbiased and they both tell us great things. So usually in statistics, if the test statistic is complete, we'll all agree. But there's other ways to show that. So i.e. you could show that there is a minimal variance out there. You could figure out what the lower bound is. If the lower bound is something different than 0, it might be useful to you. So that bound might be tight, and you might be able to attain that bound. So what I'm going to do is I'm going to bypass the part about attainment in chapter 7 and just say if you can meet the the lower bound, the theoretical lower bound, and we'll derive that. That's Kramer-Rao. You guys are imputing, half the class probably knows what that is already. If you can attain it, then it's attainable. So I'm going to skip some of the technicalities and just make it so that the testing in this class can be a little bit more streamlined, practical, and not quite so abstract. In an advanced inference class where they're invoking measure theory, all your calculus problems are going to turn into proofs. So you'll decide if you like that flavor of statistics. So it's not that it's not useful, it's probably just a little bit too steep for this point. Fair enough? So, cool. So I guess today's one of these days that I think completeness is kind of cool, but we're going to leave it as an aside. So what I would like you to know is just what the definition is. If somebody asks you what it is, I don't want you to say, Lehman didn't teach me anything about completeness, because that's not true. So I don't know, he didn't teach me anything, so I didn't cover it. You have a book, I've said things about it, I did at least introduce you to the concept. Okay. Nobody's ever going to ask. Let's move on. Let's flip the chapter and start doing some point estimation. I just want to motivate a little bit, a few different techniques, and ask some questions about the techniques. We've done all of this in the first couple days of class. We set up a problem. We looked at some different estimation techniques. We did some simulations to show maybe that our techniques were biased or what the variability is, and we looked at histograms to kind of compare techniques. All the techniques we looked at were semi-rational. They kind of all would converge asymptotically, but some were better than others in the sense that maybe they nailed the parameter with very tight variance. So they nailed it in terms of the expectation. Some of our estimators were biased, but they had very little variability, and that could be a good thing if the bias level is small. So I want to just motivate with a problem where we might all agree. So let's just consider this basic setup. I'm going to say the probability of a heads is equal to P, and the probability of a tails is equal to 1 minus P. So basic setup. Heads and tails, Bernoulli coin flipping. Everything's IID in this example. So when you're going to see some sequence, I'm going to call it S1, and S1 might look like 3, 4, 5, 6, 7, 8, 9, 10. Let's put a heads there. So you didn't see me do that. It's just some discovery of data. Lo and behold, there's some data set right there. So it's kind of something similar to what I wrote down before. We might not know whether or not this is binomial or negative binomial, so I want to just study a few estimation techniques, see if maybe we violate some principles along the way, and see if everything's okay. So maybe this data is binomial, or maybe it's negative binomial. So the difference is binomial has fixed trials. I'm going to call that K. I'll reserve N for just a minute, or maybe I repeat this sample over and over again. I look at multiple versions of this and N copies of this. So in our case, K is 10, because I have 10 dashes. If I count it right, it looks right. So fixed trials and X, the number of successes, is random. Or negative binomial where K, the number of trials, is random, and X is fixed. So different stopping criterions. I will kind of point out, just as an aside, So just take a break. You don't need to register this anywhere in your brain that's important right now. In Monte Carlo experiments, we run our for loop a fixed number of times. So if I were looking for the successes of something to try to estimate P, I might just simulate over and over and over again and then count my number of successes that I see and then divide by my number of trials, which was fixed. That would be a Monte Carlo experiment. There's another type of experiment out there called Las Vegas experiments. So the metaphor is analogous to Monte Carlo. Monte Carlo has casinos, Las Vegas has casinos as well. So they're not very similar places. Anybody been to Monaco?
My friend is there right now. She's
You got a friend?
Pictures of the casino yesterday.
I got a friend too. Who's your friend?
Her name's Linnea.
Okay. Mine's Lance Armstrong.
Friend.
Yeah, exactly. I'm just kidding, I don't know. I have met him a couple of times, he's a total jerk. So, is your friend? Your friend's a nice person.
Yeah, right.
That's surprising. Not a lot of them in Monte Carlo. So they're all tax evading over there, have yachts, all that kind of stuff. Anyway, in Las Vegas experiments, you look for some number of successes, and then you just run the simulator until you count that many successes. And you can see why that might be a good idea. If P was very, very small, I might run a Monte Carlo experiment, see no successes, and then estimate everything with 0. And if I were doing the sort of variance calculation we would do in a binomial experiment, I would say the variance is 0 too. So it's a terrible way to do things. So if P was anything but 0, you would estimate the wrong thing. So Las Vegas experiments say, I need to at least run this enough to at least see a success so that I'm not estimating 0 and saying something nonsensical. So the rub with Las Vegas is when your advisor or your boss says to you, how long is the sampler going to take to run? You say, I don't know. I'm just going to wait until it's done. I said I wanted to see 17 successes. And if P were really small, you might say, well, it's going to take 18 billion years to run this thing. So, and you're getting paid all the while running this thing, and you're like, I'm working really hard. I'll tell you when it's finished. So nobody will ever pay for you to give them an answer if you say, I have no idea how long it's going to take. There is some neat theory that can go with the Las Vegas stuff, and you can come up with probability bounds on how close you are to the truth. Where in Las Vegas, or in Monte Carlo, you're just using CLT. So averaging over things, and you use the central limit theorem. So the theory is a little bit easier to get a hold of. What I always recommend people do is change the number of runs you do, keep doubling it a few times, and make sure your answers are converging. Of course, if P was really tiny, you couldn't be sure. So I'd say any problem that you're willing to study, it's probably because P is not 0 in itself, so you better see at least one success before you answer anything to anybody. Okay, so that's just a little bit of an aside. So maybe the data is binomial or negative binomial. What I really argue is run the process a few times and make sure that's always ahead. So if it were ahead after like 20 copies of it, if it was ahead every single time, I go, wow, that's really peculiar. It's probably negative binomial. So I don't know a situation where you wouldn't actually know. So this is all kind of fantasy land. Okay, if you're a negative binomial, or I'll say binomial, so bino, what we might do, and I'm not going to justify any of this right now, what I'm going to allude to is method of moment estimation, and kind of just give us an idea and at least get something that's good. Later on in chapter 7, we'll show that not everything works great with method of moment estimators. So there is a good example where if they estimate something, they're actually estimating the number of trials in a binomial experiment, and there are cases like that where you would probably want to estimate that instead of what P is. But they co-estimate P and the number of trials, and they end up telling you that the number of trials is outside of any realistic bound. So sometimes, for example, you could have parameters that have to be positive, and method of moment estimators could give you something negative, so it doesn't ever respect the bounds. I'll say if you ever build anything up with a likelihood function, you can't do that because the likelihood function is always just going to be defined on the space of possible answers. So let's just say negative binomial, the distribution probability of x given p is equal to k choose x, p to the x, 1 minus p to the k minus x. So standard fare, all stat 101 stuff so far. Expectation of this, I'll leave off the p, but if you want to write it in, if you're as neurotic as I am, and I just feel like I have to do it a lot of times, you can do that. We all mean the same thing. This thing is equal to k times p. So probability times the number of trials is the expected number of successes. So if we expect x to be this, and I actually have one sample out of this, so I'd say in our case right here, x is 5, our empirical sample, what we've observed, I might say let's just match that to what we've actually observed, x. So that's what we get to observe in our example on the board, x is 5, k is 10. So what I can do with that is I can match these two things. So we can match. So I'm going to match the moments. This is the theoretical moment. And this one right here is the empirical moment. So empirical is just another word for observed, what we got to see. So we match them. When we match them, I'm setting up an estimation technique, and I need to tell you, I'm not talking about the true p, I'm talking about my estimated p, what I'm trying to estimate in the first place. We don't know true p. True p is this quantity that's out in the universe. We don't have it, but we're going to distinguish the truth from what we're estimating by throwing a hat over it. This is one of the less critical errors that I think people make in statistics, but since I'm a professor, I have to be harsh about it. So anytime you end up doing the match, I'm going to distinguish whether or not you put that hat on there. So as soon as you're invoking an estimation procedure, write down that it's p hat. And I'll say that's x. So then I can derive p hat is equal to x over k, and that's the number of successes over the number of trials. So no big mystery, I'm sure most of you have done this before, something like this. We looked at techniques that were kind of like this in the first part of class when we ended up looking at the expectation of that uniform and doubling it. So we looked at 2x bar, we doubled everything, and what we found out in that procedure is it was an unbiased estimator, but the variance was high. So if you recall. So this answer makes sense. I think that's a good answer. Let's just look at what happens when I get a little bit more data. So some more data. I'm going to say we're going to get S1 all the way up to Sn, so n data sets. This would be the way to distinguish whether or not it was binomial or negative binomial. I'm going to still pretend I don't know. So, but of course, if I solved replicates, I would have some strong indication. So if I thought it was binomial, then what I could do is I could look at expectation of x, match this to kp, so that's the theoretical moment. So, in this I'm going to match with, now that I have multiple copies of all of this, I'm going to match it with its empirical mean, xi divided by n. I goes from 1 to n, so this is the number of successes in k trials. So I'm just getting these different vectors of these things and I'm repeating it n times. So what do we get through matching everything? We get p hat is equal to sum of the xi's divided by n times k. How do I interpret this? Again, this is I goes from 1 to n. This is the number of successes over a number of trials. Cool. Seems to make sense. So this matches my second grade intuition. I'm pretty sure, maybe around second to fourth grade, I could have comprehended what we're doing here. So I think they had us do little experiments like that where we were throwing darts and estimating things. I don't remember if that was second grade or seventh grade or ninth grade, I just can't remember. But at some point early in my career, before I even knew anything about college, I could understand everything that we just did. I think, not sure. So Visa, could I have done it? Maybe. Could you? Not sure, okay, so we don't know, but we can at least convince ourselves maybe we have the cognitive capacity. So nothing crazy. I haven't said anything about properties on anything we've done, but we've gotten some estimator that seems to make sense to us. Let's look at the negative binomial case. So this is a little bit different. There's different ways that I could write this thing down. So I think what I did before is I looked at k minus 1, choose x minus 1, p to the x, 1 minus p to the k minus x. So this is the way I derived it for you on the board before, as I give you this formula. So k is random. So k takes on values. Where do I start with this? How many times do I have to flip the coin minimally?
X.
X. Because we're guaranteed to have X fixed successes. So I start this distribution counting at X plus 1, X plus 2. And if you think you're the only one that ever makes a mistake on this, I make this mistake sometimes that I'll write it down wrong on a problem that I give people on a midterm. I've done this before and it's like, oh shoot, I gave you the wrong bounds. And I gave you the shifted bounds or the unshifted bounds, and sometimes I make a mistake when I write this down. Anyway, I like to think of this one first because I can draw that picture and rederive this. It looks very binomial-ish, multiplying by an extra p for that last draw. There's another way of writing this down. So I'll say myself a little bit of room. Or, and these are equivalent, I could just replace k with x plus y in all of this. So that's the total number of trials. I've got my successes and I've got my failures right here. So I could replace all these arguments in here and I could write this down as x plus y minus 1. And I could choose x minus 1 right here, or I could choose y. It doesn't matter, they're the same things. So it's the complement of that. So p to the x, that part's still fixed. 1 minus p to the y. So sometimes you'll see people write it down this way. And this is the way the book seems to prefer. So that's why I want to just show you. I will try not to be tricky about this, and I'll try. I know that when you take a midterm in here, it's like 9 a.m. So I'll try to be polite and make you not think too much about this if we use a negative binomial on a midterm. So where does y go from?
Zero to infinity.
Yeah, it goes from 0, 1, 2. They're the exact same distributions. All I did was shift everything. So it's just a shift. So that's all we're doing. Here, y is random. Okay, just real quickly, who's on the ball? What's the expectation of y? I'll give you epsilon, if you know the answer off the top of your head. David, do you know? Expectation of y?
I think it's
Okay, not off the top of our head, but
P, but then I think it's multiplied by K.
so what do you think the answer?
K, then 1 minus P over P.
You're close. Anybody else? Okay, that's what I thought. So commit this one to memory. So something for your flashcards, it's x times 1 minus p over p. So you're exceedingly close, it's x instead of k. Right here. So there's different ways to write all this down right here, but that's what that answer is. Just commit that one to memory. I probably don't expect you to know this. So at 9 a.m., so I'd probably give this to you if I asked you for a problem like this. So we could go through and derive this, but I'm gonna let you do that old probability stuff and try to explain to yourself why this is true. If you knew this, what's the expectation of k? Plus x, I'm just gonna shift it. So that's just my shift. So you can go back and forth. If you know one, you know the other. And you could re-express this in terms of k, or not in terms of k. You need to express it in terms of the fixed thing. If k shows up here, you've got a problem. So that's part of the random stuff. If y would have shown up there, you've got a problem. It's got to be conditioned on a fixed thing. So that might be a good way to remember that. It's not k, because k is the random thing, or at least it's part of the random thing. So it has y in there that's random, and that can't be the answer. Anyway, this one is this, so this all depends on everything, and I just shifted it over. So that's the relationship between these two forms. So I don't know why that's so confusing early on, but I remember being kind of mentally tied on that for, I don't know, at least a year, where it's like, which one's which? After a while, you'll just remember it correctly. Let's just do the same exact thing with the negative binomial. And just look at this. So I might have the expectation of y. This is equal to x times 1 minus p over p. And then I'm going to match this to y itself. So that's going to be my observed. Keep in mind, when I write it like that, that's the random variable. When I write it like that, that's the observed quantity. So they are different y's. If you want to put a little squiggle over the top or call it observed, you can do that. Most books aren't that polite. We can solve for everything. So I can match. And I can say x over 1 minus p hat over p hat is equal to y. So let me just rewrite that a little bit. So that's going to be 1 over p hat minus 1 is equal to y over x. So all I've done is bring the x over here. And then I wrote that fraction in a slightly different form. So that means that p hat is equal to y over x plus 1 inverted. So I inverted my p hat over there, brought over the 1. I can rewrite that 1 as x over x, so this is easy to combine. And so this thing is going to be x over y plus x. You could rewrite that down as x over k, and lo and behold, you have the exact same answer. So this is the number of successes over a number of trials. Just make sure that nothing weird happens. Let's look at some more data. Let's imagine we got copies so that we could at least distinguish if we're in the negative binomial or binomial case. Truth is you could never know for absolute certainty. which case you're in if you're just finding these data sets around. So it's a little unrealistic. Usually you would have some control over how you did the experiment. So if I saw more data for the negative binomial, I am going to see S1 up to Sn. So I have some different copies. I'm just going to look at the expectation of y. This is still going to be x times 1 minus p over p. That part's the same. But now I'm going to use my multiple copies of things to do all my estimation. So I'm just going to look at sum of the yi's divided by n. I goes from 1 to n. These, again, are the number of failures for each of my n SIs. A lot of times I'll write this like this. I goes from 1 to n. So that means the same thing as that. And I can solve for p doing this sort of thing after I match. And lo and behold, you won't be surprised what happens. So I guess we could do the math. Give ourselves a mental break. Just do some algebra. So this is going to be x, 1 minus p hat over p hat. So I'm setting up an estimation technique. I'm saying that is equal to sum of the yi's over n. I could divide by my x's again. I could do the exact same thing and say p hat is equal to sum of the yi's over nx plus 1 invert. So same sort of manipulation that I did before. I'll change this to n over x, so I can combine these, and maybe I want to make this ki minus x. So same exact thing, so that's yi. Right there. So I'm going to sum this up n times. You can see what happens. It's going to cancel that one. So this is going to be sum of the ki's over nx. Inverse, yeah. Thank you. What I meant is you guys can relax. I'll do algebra and mess it up on the board. So what is this? This is number of successes over number of trials. So nothing went wrong in any of this. Everything worked great. Let me just ask a quick question. Are we giving biased or unbiased answers? For P. Should be quick. It should be immediate because of what we just did. Unbiased. And the reason why is because I matched at the first moment. So I designed this to be unbiased. I didn't have to match the first moment, and I could have matched second moments. And if I did that, I would be unbiased in the second moment. Now, I'd probably have a trade-off. A lot of times we want to be unbiased in the lower order moments. So, because they have more to do with the distribution itself. Think about moment generating functions, how they kind of cascade and how those moments kind of order each other. So if you're thinking about Taylor expansions or something like that. Okay, so everything went great. Let me just ask this quick question. Did we violate the likelihood principle? Yes. We didn't even look at the likelihood function. We didn't derive everything through the likelihood function. So the answer is yes because of the technique we used. We matched moments. We didn't even pay any attention to the likelihood function. Is it a problem? I'll give you the answer. No. No problems here. So answer is yes. And I'll just ask another question to compare. And that answer can be anything you'd like it to be. We did violate, we have reasonable answers. Let me just look at a slightly different technique and we'll pick up with this next time. We'll complete this story and we'll keep asking this question. So let's look at max likelihood. I kind of like max likelihood estimation because there's not choices for me to make on like which moments do I match and likelihood principle and all that stuff. I can maybe just think likelihood seemed like a good idea. The max likelihood is the maximizer of that likelihood function. So it's not the maximum point of that, it's the value that maximizes that position. So it's the argument that maximizes the likelihood function. Let's just do this with one data point, just real quick. So I can look at likelihood P given X. If I was thinking binomial, and this would just be, and I hate doing this, K choose X, P to the X, 1 minus P, I'll write it as K minus X right here. I hate writing equal right there. I could write proportional and just get rid of everything, but just let's leave it in as equal. You see a lot of people do that. Instead of working with the likelihood function, I'm going to work with the log of the likelihood function. So log, which is monotonic. Monotone functions do stretch the space, but they preserve the minima or the maxima. And they taught you that in calculus class. So the log likelihood of P given X is equal to, I'll just do some simplification. K minus X log 1 minus P plus logarithm of K choose X. The reason I wrote equal sign there is because I have to write something here once I do this. There is no symbol out there to say I can add on a positive constant or add some constant, and that would be the analog. I really wish they came up with a new symbol. I'm going to call it like that. So there is no symbol like that. I wish I could invoke that symbol and say add on a positive constant, because I like working with log likelihoods and I don't have a symbol for it. So what do? I just swallow it. And I just call it equal here and I call it equal there. What we'll figure out is this part doesn't matter in the first place. So if I take a derivative of the log likelihood, this is going to be X over P plus K minus X. Derivative of that is 1 minus P, chain rule. Hopefully you can do that. Plus 0. So it never even matters in the first place. So most people just omit that from the very, very beginning. And I can solve for P. So what I might do is be tempted to set this thing equal to 0. Don't do that until you throw a hat over everything. K minus X, 1 minus P hat is equal to 0. So by setting it at equal to 0, I'm trying to find the maxima of the distribution before we just found the derivative. So P is the right thing to talk about. And as soon as I set it equal to 0, I've invoked an estimation technique. So at the end of the day, I can solve for P. We've already done exactly this. So I'll just write down the answer. This is going to be P hat is equal to x over k, and that's the number of successes over the number of trials. Look at all this agreement. Let me just ask a question. Did I violate the likelihood principle by doing this? Feeling your blood boil. Dylan?
I don't think so.
No, we didn't. So we used the likelihood function, we adhered to the sufficiency principle and the conditionality principle that we got for free out of all of those things. So likelihoods are always conditioned on the data, so it's conditioned on the sufficient statistic. If I work through the example with more x's, just like I did over here, you would get the same exact answer that we got before. So I just product together all this stuff, put i's on all my x's, and as I took the product, that would extend to the exponent, and I'd be summing up those x's. And that would be my sufficient statistic. It would automatically just appear because I used the likelihood function. So let's just leave it with this question. Did we violate the likelihood principle? I'll call it LP, and the answer for maximum likelihood estimation is no. And this is the part that people are so constantly arguing about. It's like, what do you mean? That estimator didn't violate the likelihood principle here, but it violates the likelihood principle. So the likelihood principle is not about the answer. It's about what you are thinking about as you derive the answer. So you can already just think about how often that could create an argument, because people can't distinguish those two things. So if you've ever been in an argument before, you're always like playing semantics with the other person. No, what you said was this. So, but you guys might be agreeing with each other. So I used to like that sort of thing. I think that's what I liked about the likelihood principle, is I could get into a technical debate with somebody and act like I was winning it. So all the while I'll be losing that argument for 20 years, is what the reality is. So the likelihood principle is a little bit different than what your answer is going to be given. What I think about the likelihood principle is it's guardrails. So to kind of keep us in bounds, and that's a good idea. So the likelihood principle, or at least likelihood functions, are a good idea, but I don't think it's the only way to come up with good answers, and that's what people are debating about. So do you have to operate your life with guardrails? I hope not. So sometimes it's fun not to do it. Let's just see what will happen. So enough on philosophy. Let's come back to Bayes, see what a Bayesian does. I'm going to omit the part about the negative binomial, because all that would have changed is the normalizing constant. And as soon as we took the derivative, that went to 0 anyway. So the negative binomial answer, in the binomial answer, you get exactly the same answer because you're using the exact same likelihood function. And that can be a nice part of the likelihood principle. That if we all agree on the likelihoods, we will get the same answers if we're adhering to the LP. So maybe it's a good idea, it's a good way of practicing the sufficiency principle and the conditionality principle. We can see what goes wrong. If you don't, but not always is something going to go wrong. So sometimes it can work out. And arguing for that, I'll just let you know, is pointless. So whoever you're arguing against is they're never gonna swallow that. So I have 20 years of experience. Really more like 18, but we'll round up. That's it for now. We're gonna try to justify more about this. I'm just exposing you to things that I think you kind of know a little bit. But the whole point of chapter 7 is to show the properties of these different techniques. So we'll run through this with Bayes, just as a quick reminder. I'll generalize method of moments. I'll try to generalize maximum likelihood. I'll say things like they said in your first calculus class, that it's not good enough to just take the derivative, set it equal to 0. You need to check to make sure that thing is a maximum. It's a global maximum. So you're going to need to do things like maybe the second derivative test in disguise if you like doing things that way. You could just use different incarnations of the first derivative test and use the mean value theorem if you like to do it that way. So see if the signs on everything changed, and if the signs on the tangent changes, you just went over maxima or minima. You need to check things at the endpoints as well. So the book says all that. They use a two-dimensional example to describe it, and they say some things about eigenvalues. What they're really describing to you, if you read that part of the book, is the second derivative test in disguise. So I'll regurgitate a little bit about what's going on in the book, and then we'll start leading into some theory. So if you want to get ahead on what the theory is, look up Kramer-Rao. That will be one of our more complicated proofs. And I guarantee you, I will ask you to prove that in this class. What did I just say?
Don't worry about it.
Yeah. Okay. Somebody that isn't as sarcastic as me.
Next exam.
It's on the exam. It's guaranteed to be at least on one of the next two exams. So put that in your back pocket. And then also Ralph Blackwell, I like that one too. So that's the easiest proof in probably the whole book. So glance at that and see if you know what it says. But Kramer-Rao is the one you might want to spend some time getting ahead. If you're thinking, you know, I just want to study a mechanical proof, do some calculus, just feel like doing that for an hour or two, Kramer-Rao, jump straight to that. And you'll have a lot of the answers that I'm going to be leaning into. Thanks for your patience, you guys. I think tomorrow we'll definitely do a review session. It will probably be Mohammed. Did he answer already? I didn't check the Slack this morning. He said yes, right?
He said yes, but he wants to reserve the room.
Yeah, he's confused. Let me get him straight and say that it's here at 6 p.m. and then all of us will be aligned. And then what I think I'll do is I'll come back the Thursday after and do another review session. So just to clear up some things. So you get a couple different perspectives on it. Cool. And Mohammed's taken the class. This is his second time TAing. So he knows what the answers to your questions are about the project. Because I leave a lot of open-ended stuff in there. So do something reasonable and you'll be able to answer whether or not it's reasonable. I'd like you to make choices. Cool. That's it for now. Thanks so much.